Hello and welcome to G Fun Facts Online. We're all familiar with the plastic crisis. We see it in images of polluted oceans and overflowing landfills. It's a material designed to last forever, and that's become its biggest curse. For decades, we've been told that recycling is the answer. But what if our current methods are failing us? Today, we're not just going to talk about the problem. We're going to explore a revolutionary solution emerging from the world of chemistry. A technology that doesn't just recycle plastic, but upcycles it, transforming trash into treasure. This is the story of catalytic upcycling. First, let's be honest about the state of plastic recycling. The system we know, called mechanical recycling, is where we sort, clean, melt, and remold plastic. It sounds good in theory, but it's incredibly limited. The process requires meticulously sorted, clean plastic streams. Even a small amount of a different plastic type, a leftover food label, or a bit of dirt can ruin the whole batch. The result is often downcycling. This means the recycled plastic has inferior properties compared to the original. A clear water bottle doesn't become another clear water bottle. It might become a park bench, a piece of carpet, or a speed bump. It's a one-way street to a lower value product, and eventually, the landfill. Because of these challenges, a huge amount of plastic waste is simply deemed unrecyclable and is either incinerated, releasing greenhouse gases, or buried in the ground forever. But what if we could hit a molecular reset button? This is where chemical upcycling comes in. Unlike the physical smashing and melting of mechanical recycling, chemical upcycling operates at the atomic level. It uses special substances called catalysts. Think of catalysts as molecular facilitators. They speed up chemical reactions without getting used up themselves. In this case, they are used to precisely break down the long, tangled polymer chains that make up plastic into their original building blocks, called monomers, or into other small, valuable molecules. These building blocks are identical to the ones derived from fossil fuels. They can be used to create brand new, virgin-quality plastics or a whole range of other high-value products like fuels, industrial lubricants, and specialty chemicals. This approach can handle the mixed, messy, contaminated plastic waste that mechanical recycling can't touch. And by creating valuable products from waste, it creates a powerful economic incentive to actually go out and collect that waste. It's a key step towards a true circular economy, reducing our reliance on fossil fuels to make new plastics. So how does it actually work? Scientists have developed a whole toolkit of catalytic methods, each tailored for different plastics and different outcomes. Let's dive into the three main techniques: pyrolysis, hydrogenolysis, and solvolysis. First up is pyrolysis. The basic idea is to use very high temperatures, typically over 400 degrees Celsius, in an oxygen-free environment to thermally crack the plastic polymers. It's like cooking in a pressure cooker on a massive scale. Without a catalyst, this process can be inefficient, requiring a lot of energy and producing a complex, tar-like soup of different chemicals. But when you introduce a catalyst, everything changes. Catalysts can dramatically lower the temperature needed, speed up the reaction, and, most importantly, steer the reaction to produce specific, valuable chemicals. One of the superstar catalysts in this area is a class of minerals called zeolites. These are microporous materials, meaning they have a sponge-like structure at the molecular level, with tiny, precisely sized pores. By tuning the size and acidity of these pores, scientists can selectively crack long polymer chains into smaller, more desirable hydrocarbons. For example, a specific zeolite known as HZSM5 is incredibly effective at converting common plastics like polyethylene and polypropylene into benzene, toluene, and xylene, a group of chemicals known as BTX. BTX are fundamental feedstocks for the entire chemical industry, used to make everything from nylon to synthetic rubber. Of course, it's not without its challenges. One major issue is catalyst deactivation. where a carbon residue, or coke, builds up on the catalyst's surface, clogging its pores and stopping it from working. Researchers are actively developing better ways to regenerate these catalysts, for instance, by carefully burning off the coke to restore their activity. Our second major technique is hydrogenolysis. The name gives a clue: hydro for hydrogen and lysis for splitting. This process uses hydrogen gas along with a catalyst to cleave the incredibly strong carbon-carbon bonds found in plastic polymers. It's particularly effective for upcycling polyolefins, like polyethylene, the most common plastic in the world, which is notoriously difficult to break down because it's chemically very inert. The catalysts here are often precious metals, like platinum, palladium, or ruthenium, spread thinly over a support material. The process transforms plastic waste into a range of valuable liquid hydrocarbons, including high-quality, clean-burning fuels and premium lubricants. A key advantage of hydrogenolysis is that it produces saturated hydrocarbons. These are more stable and have a higher energy content than the unsaturated products you often get from pyrolysis. It's like turning a plastic bag into high-grade diesel fuel or synthetic motor oil. The big breakthroughs in this area are now focused on cost. Precious metals like platinum are expensive, but recently studies have shown that inexpensive, earth-abundant metals like nickel can be used to create highly effective catalysts. One new nickel-based catalyst has demonstrated the ability to break down mixed polyolefin waste without extensive sorting, a massive step forward. It even showed a remarkable tolerance to contaminants like PVC, which would normally poison and destroy other types of catalysts. Our third tool is solvolysis. This method uses solvents, often boosted by a catalyst, to chemically deconstruct condensation polymers back into their constituent monomers. The most famous example is polyethylene terephthalate, or PET, the plastic used for beverage bottles and food containers. Using a process called glycolysis, which uses ethylene glycol as the solvent, PET can be cleanly broken down into its monomer, a chemical called BHET. This recovered monomer is identical to virgin monomer and can be repolymerized to create brand new PET plastic. This is the holy grail of closed-loop recycling. The new plastic is so pure it can be used for food contact applications, something that is very difficult to achieve with mechanically recycled plastic. This same principle can be applied to other plastics like polyurethanes, found in foams and insulation, breaking them back down into their valuable chemical precursors. And the innovation doesn't stop with those three. The field is constantly evolving. Researchers are now exploring even more futuristic approaches. One is photocatalysis, which uses light energy to drive the chemical reactions. By using semiconductor materials like titanium dioxide as photocatalysts, scientists can use sunlight to break down plastic waste into fuels like hydrogen gas and other useful organic chemicals. It's a greener alternative to the high-temperature processes, though it's still in the early stages of development. Another exciting frontier is electrocatalysis, which uses electricity to drive the conversion of plastic waste. This can be done under mild conditions, at room temperature and pressure, offering high precision and control. For instance, researchers have used it to convert PET plastic into formic acid, a valuable commodity chemical. The most exciting part? If you power the process with renewable energy sources like wind or solar, you could have a completely carbon-neutral pathway for upcycling plastic waste. As promising as all this sounds, the road to widespread commercialization is filled with challenges. We can't just ignore the practical hurdles. First, there's the feedstock problem. Real-world plastic waste isn't a pure stream of one polymer type. It's a chaotic mix of different plastics, colors, additives, and contaminants. Developing robust catalysts that can handle this mess without being poisoned is a major research focus. Second, as we mentioned with pyrolysis, catalyst deactivation is a serious issue. For these processes to be economically viable, the catalyst must either last a very long time or be easily and cheaply regenerated. Finally, there's the challenge of scale. Proving a process works with a few grams of plastic in a lab is one thing. Building a massive industrial plant that can process thousands of tons of waste per day is a monumental engineering task. Then there's the economics. Techno-economic analyses are underway for all these technologies. While they can produce high-value chemicals, the overall cost, including collecting and pre-treating the waste and the energy needed to run the process, can be high. However, just like with solar panels and batteries, costs are expected to fall dramatically as the technology matures and we achieve economies of scale. From an environmental standpoint, it's a clear win over landfilling or incineration. But we need to conduct full life cycle assessments to ensure the energy used in chemical recycling doesn't create a different environmental problem. The goal is a net benefit for the planet. To make this revolution happen, technology alone isn't enough. We need supportive government policies. This could include financial incentives like tax credits to encourage investment in new recycling infrastructure. It could mean recycled content mandates, which would require new products to contain a certain percentage of recycled material, creating a guaranteed market for these upcycled chemicals and plastics. And clear, consistent regulations are needed to give companies the confidence to make long-term investments. The great news is that this is not just a dream in a research lab. A growing number of companies are pioneering this new plastics economy. Honeywell has developed its upcycle process technology and is partnering to build a facility in Spain to process mixed plastic waste. LyondellBasell, one of the world's largest plastics companies, is building an industrial-scale catalytic recycling plant in Germany using its proprietary technology. Chemical giant BASF has launched its ChemCycling initiative, using pyrolysis to turn plastic waste into feedstock for its own production. These are just a few examples of a massive industrial shift that is already underway. So where does this leave us? Catalytic upcycling represents a profound paradigm shift. It's a move away from viewing plastic as disposable trash and towards seeing it as a valuable, above-ground resource. By breaking plastic down to the molecular level, we can escape the downward spiral of downcycling and create a truly circular economy for plastics, one where we use, remake, and reuse indefinitely. The journey will be challenging, requiring continued innovation in chemistry, engineering, and policy. But the potential reward is a solution to one of the most pressing environmental crises of our time. The chemical solution to the plastic crisis is no longer a distant hope. It is a tangible reality taking shape in labs and industrial plants around the world, turning our waste into the building blocks of a cleaner future. Thank you for tuning in to G Fun Facts Online.